Hello everybody, welcome. This is May 2023, paper 2, and it's from time zone 1. Let's have a look and see what we can do. Okay, first mark is a 15-mark question. Let's have a read. The mean annual temperatures for Earth recorded at 50-year intervals are shown in the table. Tammy creates a linear model for this data by finding the equation of the straight line passing through the points with coordinates 1708, 8.73, 1958, 9.45. First question, part A, asks us to calculate the gradient of the straight line that passes through these 2 points. So we've got these 2 points right here. This is our data set, which relates year and temperature. So we have different years through time, and then the corresponding temperature at that given time. All right, calculate the gradient of the straight line that passes through these 2 points. Nice way to get started, I guess. Gradient formula, remember, is in your formula booklet, and I'll just bring that up right here. It should be under functions, so topic 2, and here we go, 2.1 gradient formula, m, that's our slope, and then it's y2 minus y1 over x2 minus x1. Essentially change in y over change in x. So let's go back to the document, write that out, and calculate the gradient. So m, this is for part A, m is y2 minus y1 over x2 minus x1. Sometimes it's helpful, if you want, you can label these values. This is one coordinate pair, x1, y1, and this would be x2 and y2. After that, we can just go ahead and substitute. So y2 is 9.45 minus 8.73 over x2 is 1958 minus 1708. Okay, let's go ahead and calculate this. Just bring up the calculator screen. Here we go. And let's solve. Okay, let's get a fraction. 9.45 minus 8.73 over 1958 minus 1708. Okay, going back to the document. Actually, here we have 0.00288. All right, so let's go back to the document and write this out. 0.00288, and that's already to 3 sig figs. Okay, part B. Part 1 of Part B asks us to interpret the meaning of the gradient in the context of the equation. So here is Part B. So we know that the slope of a line is given by change in y over change in x. And sometimes we write this as change in y over change in x. So more conventionally, if you've ever seen, let's say, just a coordinate grid, for example, with 2 variables. In this case, we know y. This y-axis right here, oops, look at this back. This y-axis right here is degrees Celsius, and this x-axis right here is given by time. So if slope itself is just the rate of change, that is to say for one change in, let's say, 1 year, unit time, what is our increase in the y dimension? So if we're talking about change in y over change in x, our y-axis is temperature, and our x-axis is time. So what we have is change in temperature over change in time, or just in more plain language, we have change in temperature per unit time. So this would be change in degrees Celsius per year. State appropriate units for the gradient. So this would be part 2. Part 2, appropriate units. So if we're talking about, once again, change in y over change in x, we're talking about degrees Celsius per year. That would be fine for our units. So if we have 0.002 0.0288. What we actually have is 0.0288 degrees Celsius, degrees Celsius per year. And that's what this slope means, this gradient. We know that we change by just a small fraction of a degree every single year, according to our model. All right. Part C, find the equation of this line giving your answer in the form of y equals mx plus c. All right. So we have a slope already. We have a value of m. Let's go ahead and write this out for c. We have an equation of a line which is equal to y equals mx plus c, and we already have m, so we have y is equal to 0.00288 x plus c, and we know mostly everything here. Well, we know our slope, but we don't know what the value of c is. We don't know our y-intercept in this case for an equation of a line, but we do have two sets of points. We have one point on the line, that is to say one xy value, and we have another xy value. So we can substitute either in and then solve for this unknown right here. So let's go ahead and do that. Let's take just the first value, I suppose, this one right here. So our y value is 8.73. 8.73 equals 0.00288, and we're going to substitute this y value right here, this x value right here, this x value into our equation of 1708, and then now we can solve for the unknown. So now we've got an equation with just one unknown, and we can go ahead and use a little algebra if you want, or we can just solve this for c. Okay, so let's bring up the calculator and work this out. Let's go algebra, numerical solve. So let me get this up. Menu, algebra, numerical solve. 8.73 equals 0.00288. Open up a bracket, 1708. And we want to say plus c. We don't know what this is. And then, of course, ask the calculator what to solve for. There we go. So our value of c looks to be 3.81096. So let's go back to the calculator and write this out. So we know c is equal to 3.81 to 3 significant figures, and now we have an equation of a line. So that was this last missing piece of the puzzle. So let's go write that out. 3.81, that's our value of c. This is our equation of a line. Y is equal to 0.0288, our slope, plus our y-intercept, which we found by substituting. Okay. Use Tammy's model to estimate the mean annual temperature in the year 2000. So the average temperature in the year 2000. So we've got this equation of a line right here. Whoops. We've got this equation of a line, this right here, and it relates inputs, so years, to a given temperature at that year, or the average temperature at that year. So let's go ahead and substitute this value of 2000 and see what the model would predict. So we have y is equal to, this is part D, y is equal to 0.00288x plus 3.81, and we know we're trying to predict temperature in the year 2000. There we go. So I'm actually just going to work this out on the calculator that I have beside me. That would give us a value. 288 times 2000 plus 3.81. And by our model, we would predict that it would be 9.57. And that's the value that the calculator gives, so no rounding required. Okay. For a question like this, you might want to see if it roughly corresponds with what we have already in our model. So we know 2008 is 9.76. This value of 9.57 degrees Celsius looks to be a pretty good prediction and might suggest that we're on the right track. Okay. Thandiso uses linear regression to obtain a model for the data. So really what we have, and often one of the challenges with paper 2 is interpreting what it's asking. So this question doesn't seem too bad, but when it's seen all at once as a 15-mark question, it's somewhat, or sometimes a little difficult to see what a question is asking. And in this case, the whole question can be broken down, at least I think, into two parts. That is to say, there's two individuals, Tammy and Themiso, trying to create a model to map or to create an equation that maps a year to a given temperature that relates these two variables. And Tammy chooses 2 points on the line, finds the gradient, substitutes a point, and then she's kind of found this in kind of an arithmetic way, I guess, or you might say like kind of an old-fashioned way. And this is what her model predicts. And then the second part of this question is Thandiso, and he's going to run a linear regression, and he's going to create a model using, in some sense, what's called a sum of least squares method. So he's going to use his calculator to solve this. And the question, I think, can be broken down that way. All right, so Thandiso uses linear regression to obtain a model for the data. Find the equation of the regression line y on x. So this is part E. Find an equation of the regression line y on x. For this, we'll go into the calculator and use spreadsheets and run two variable statistics. So let's go to the calculator and work that out. All right, menu, spreadsheets, and we'll input the data that we have in our original table. So if we have x and y, x, this corresponds to our years. So 1708, 758, and these were just at 50-year intervals, 1958, 1908, 1958, and 2008. And then we have the corresponding temperatures at those given times. So 8.73, 9.22, and so on. 13, 9.45, and 9.76. All right, sometimes it's not a bad idea to check these over. 0.1, 12, 13, 45, 76, and these are all 50-year intervals. Okay, so after this, if we want to create a linear regression, we'll go Menu, Statistics, and we want to go Stat Calculations, and in this case we have two variables. We're relating time and temperature. So two variable statistics, tell the calculator where you put the x, where's the y. That's all we need to do for this. And then we can go down and, oh, I'm sorry, two variable statistics is actually incorrect. What we want to do is run a linear regression. Here we go, linear regression, y equals mx plus b. There we are. Okay, so we're looking for those values once again of m and b, or what we called m and c early on. And here they are. So there's our value of our slope, and there's our y-intercept in this case. Okay, so let's go back to the document and write these out. So find an equation of a regression line y on x. We're going to have this equation of a line as y equals mx plus c or b, doesn't really matter. And let's use b since that's what our calculator has given us. And we have y is equal to, and just reading off from the calculator, we have m as 0.00, and it's given us 2557, so we'll round that to 2557, 256, x plus, and the value of b was 4.464, so we'll round that to 4.46. Okay. Find the value of r, the Pearson's product moment correlation coefficient. This is actually already given to us. So let's go back to the calculator screen. So we can do two variable statistics, but this is actually given to us when we originally calculated a linear regression. And here it is. This is our r value right here. So let's go back to the document. Actually, here it is. Let's read it off. 0.8613. So going back to the document, r is equal to 0.8612, three significant figures. Okay. Part F. Use Thandiso's model to estimate the mean annual temperature in the year 2000. So here we have f. So what does this model predict in the year 2000? So here's our equation of a line once again. 0.00256x plus 4.46. And now we have some input x. Let's substitute into this equation 0.00256, and then we'll put 2000 in here. We'll substitute in for x, and then we'll ask ourselves, what is the output, the temperature at that year? What would it predict? Okay, so that's more straightforward, kind of just calculations. I'm going to work it out on my calculator right here. 2000 plus 4.46. And this would give us a value, y is equal to 9.58. So 9.58 degrees Celsius. Okay, so not too bad of a question. Maybe interpreting what it's asking might be the challenge, but if you can get past that step, then perhaps not a bad question. All right. Thandiso uses his regression line to predict the year when the mean annual temperature will first exceed 15 degrees Celsius, so when it will first be larger than 15 degrees C. Part G asks us to state two reasons why Thandiso's prediction may not be valid. So let's write G right here. So two reasons why Thandiso's prediction might not be valid. First thing is, if he's trying to predict when it's 15 degrees Celsius, we see our model, its endpoint right here once again. It ends off at the year 2008, and it ends at temperature 9.76. And what Thandiso wants to do is he wants to predict when we might expect to reach this mean annual temperature of 15 degrees Celsius. So let's just write this out really quick. This is y, this is x, this was degrees Celsius, and this was time. And really what we have here is we have a set of values right here. And if we're looking at this, we usually have what Thandiso is trying to do is he's trying to ask the question, what would the year be? What time would we have this temperature of all the way up here of 15 degrees Celsius? And the problem is that anything beyond this interval that we've collected data within, anything beyond this point is now called extrapolation. So this is something that would not be legitimate. This is extrapolation. Anything beyond our data set, any value, if we're trying to make a prediction beyond this, is extrapolation. Why is that? Because we don't know if the data is going to continue and it's linear, or we don't know if it reaches some kind of asymptote, for example, and it just tapers off. So it's not legitimate. We have what's called extrapolation. There's no guarantee that this trend will continue. So one reason would be extrapolation. That's why it would not be justified. The other reason is a little more complex, actually. What Thandiso is trying to do is he's trying to relate a y value right here, this 15 degrees, to an x value. So he's trying to relate an output to an input. And when we use a regression line to calculate or make a prediction, what we often do is we would use an input to map to some output. And there's no guarantee that we can necessarily go the other way. That is to say, we can start at our output and go to our input. So how could we potentially write that out? Cannot always reliably make a prediction from y to x. You might say cannot predict reliably from y to x, or from output to input potentially. That would be the second reason. All right. Okay. Question 2, 16-mark question. here we've got a function. Consider the function f of x is equal to 3x minus 1 plus 4x to the negative 2. So raised to the power of negative 2 right here. Part of the graph of y equals f of x is shown below. Here's our graph. The function is defined for all values of x except for some value when x is equal to a. Write down the value of a. That's our first question. So we've got this original function here. It's f of x is equal to 3x minus 1 plus, and this 4x to the negative 2. If we have x to the negative 2, what we actually have is 1 over x squared. Just like when we're doing calculus, for example, and they give us a function like 3 over x, we would write this out as 3 to the x to the negative 1. 3 times x to the negative 1. In the same way that we have this 4 times x to the negative 2, or to the power of negative 2, what we actually have here is a fraction. And so we can write this last part as 4 over x squared, essentially. And that will be useful for us here. We can also solve this graphically, writing down the value of a. So it says our function is defined for all values of x. That is to say, we can put in any value of x that we want into here, except for one single value. And since our function is f of x is equal to 3x minus 1 plus 4 over x squared, there's some value that we can't actually put in. And that's when x is equal to 0. Because then at that point we have 4 divided by 0, which is illegitimate. It's not something that we can actually solve for. Another way to possibly look at this is just graphically. You can ask, where is our vertical asymptote? So we approach infinity here as we move from the left to right, and then again as the right to left, and it approaches some value. And just by inspection, this isn't necessarily like the rigorous way to solve it, but if we're looking at this, when the value is x is equal to 0, it looks like at this point we're reaching infinity, and we're not actually going to have a value at this point. It's going to approach some value. It's going to approach positive infinity, but we're not actually going to reach some value. So write down the value of a, just one mark question, when a is equal to 0. More algebraic answer is, well, because when a is equal to 0, or when, let's say, x is equal to 0, we're suddenly dividing by 0, which we can't do. But just graphically, you can see that there's this value that we approach and don't reach. Alright. Part B, use your graphic display calculator to find the coordinates of the local minimum. 2-mark question. Not bad. Let's go to the calculator and work this out. Let me get a new document. Alright, let's go into the graph calculator and graph this function. So 3x minus 1 plus 4x. And the calculator will accept this. We don't need to write this as 4 over x squared. We can write 4 times x to the negative 2. Right, so there's our function. Don't need to do any kind of zoom fit. And let's find the local minimum. So let's analyze graph. Let's find the minimum and see where it occurs. So when x is equal to 1.39, the y value is 5.24. All right. Let's go back to the document and write that out. So they're asking for the coordinates, so let's put both the x, y values. That would be when x is equal to 1.39, y is equal to 5.24. Okay. Next part, the equation f of x is equal to w, where w is some real number. So you can read this as, it actually is an element of the real numbers, but is, and then some real number. And a real number is anything that you could put on a number line. So 0, it could be 1, 2, 3, 4, it could be root 2, it could be anything that you could put on a number line, from negative to positive infinity. So we're looking for some equation where our function is equal to w, and we have 3 solutions. So this is kind of maybe a question that tests terminology or understanding of terminology in functions. Really, when we're talking about a solution, solution of our function with some value, we're talking about graphically intersection points. So if this is our function right here, f of x is equal to 3x minus 1 plus 4x to the negative 2, what we're asking is, what's this value of f of x? What is this value w? What is it in this case? What is it in this case where we'll have three values of x, where we'll have three solutions? So three values of x. And in this case, graphically, if we look at our original function, in this case, let's draw one line, for example. This would be y is equal to 3, or in this case, w is equal to 3, and there's only one solution, there's only one intersection. Often IB questions lead into each other. They just asked us to find the coordinate of this minimum point, for example, right here. And if we look and we were to graph, let's say, any other line for w in this case, if we suddenly graph, let's say, y is equal to 7, now we have 1, 2, 3 solutions, or 3 x values. We have x1, this is x2, x3. We have 3 x values which will provide a solution, which will produce an output of 7 in this case. And really, if we want to answer this question, identify one possible value of w, it's anything above this point, this y value of 5.24. That's the minimum. Anything above that. So we could say that w is equal to 7 or something like that. Really anything above 5.24. Okay. Part D asks us to write down whether the value, the line y equals mx minus 1 over 4 is tangent to f of x when x is equal to negative 4. Write down whether the value of m is positive or negative. Justify your answer. So the line y is equal to mx minus 1 over 4 is tangent to f of x when x is equal to negative 4. Write down whether the value of m is positive or negative. Justify your answer. Okay. So we've got this function right here. It looks like this, and then kind of goes down like this. And what they're saying is there's some point when x is equal to negative 4. So when x is equal to negative 4 at this point, negative 4, actually let's change that just to make it map on a little more. When x is equal to negative 4, the question is, what is the slope? And we have negative 4 here, and who knows what y value it is? We can find that. What is m? What is the slope of this tangent line? Okay. Is it positive or negative? Justify your answer. And in this case, it doesn't seem, I actually looked at the mark scheme earlier, and a graphical solution of just graphing it and seeing whether it slopes upwards or downwards won't actually be a mark in this case. We want us to do some kind of algebraic work. So this is the slope of the tangent line. Y is equal to mx minus 1 over 4. They tell us it's tangent to our function when x is equal to negative 4. Write down whether the value of m is positive or negative. One thing we can do is we can look at our original function and we can find the derivative, that is to say the slope function, and we can input this negative 4 and ask, okay, well, what is the slope at this given point? So our original function itself was f of x is equal to 3x minus 1 plus 4x to the negative 2. And it's nice because they already gave us this to the negative 2. And one way we can do this is we can just find the derivative. And 3x to the negative 1, 3x to the 1 just becomes 3. Constants just disappear. And then dealing with this value right here, we'll multiply by negative 2. So this would give us negative 8x, and this was negative 2, and now it should be negative 3. This isn't a heavy calculus question, so I'm not going to go over the derivative rule. It's in your formula booklet. Actually, I guess I'll write it down here. F of x is equal to x to the n, f prime of x, that is to say the derivative is we're multiplying by the exponent, and the exponent decreases by 1. If we have just x, it disappears, constants just become 0, and then we can follow that rule for this last term right here. And so that is our derivative function. Our derivative function is also something that allows us to find the slope at a given point. It's also called our gradient function. So we can find the value of -4 at this point. We're asking the question, okay, well, what is the slope when x is equal to -4? And we can put this into the calculator. Actually, that's what I'll do here. So we have 3 minus 8, and then we have -4, and we raise it to the power of -3. We find out that it's positive. So going back to the document for a sec, we know that f prime of -4 is equal to 25 over 8, and that means this is our slope. This 25 over 8 is our slope when x is equal to -4. So right here we know that m is equal to 25 over 8 at this point. And so it is positive. That's one way to work it out. Another way, which doesn't require calculus, is just looking at this line itself. This y is equal to mx minus 1 over 4. And they give us an x value of -4. So we could put that in. And if we know an x and y value, then we know 2 out of the 3 unknowns, and we can solve for m. So let's go ahead to the calculator screen once again. And this is our function. And let's ask the question, going to graph trace, what is the value when x is equal to -4? And so, I mean, like we can see right here that it's positive. The slope is positive. It's going up. But working it out algebraically, when x is equal to -4, y is equal to -12.8. So we can substitute those values into our equation, and we actually just have m left as an unknown, and then that would give us a value of m. So going back to the document, let's write this out. We have y is equal to mx minus 1 over 4. And on the calculator we found out that y was equal to -12.8 when x was equal to -4. And now we have an equation where we just have some equation in terms of just one variable, just in terms of m. And we can go ahead and end solve this. That's actually what I'll do here. So back at the calculator screen, menu, algebra, numerical solve, and we'll go -12.8 equals m times -4 minus 1 over 4. I'm just going to put that as 0.25 and ask the calculator to solve for m. Oops. The error function is not defined. Okay. So something went wrong. Y is equal to -12.8 when x is equal to -4. Okay. Y is equal to -12.8 when m is equal to -4. Function is not defined. So what they're saying is that there's going to be no value there. But I don't believe that's true. So it's possible that it's not liking this. Let's see if that helps. Okay. That's interesting. 3.1375, which as a fraction gives us 25 over 8. So once again, the important thing is just that this value of m is positive. So m we found is positive. Write down whether the value of m is positive or negative. M is positive. So going back to the document here, m is equal to 3.1375, and we know that it is positive. Okay. So kind of a tricky question. There's a lot of, I guess, terminology This one requires some understanding of asymptotes, I guess. So lines that we approach but never reach. This one requires an understanding of what are solutions, so intersections between two functions. This is an interesting question that would require either some calculus to find the gradient function or the slope of a line at a given point, or just knowing that, okay, we have an x and a y value, how can we solve for m, this missing value? If we have 2 out of the 3 unknowns, can we find it? It's interesting that they wouldn't accept a graphical solution, even though it's clearly positive, right at -4, for example. Alright, let's continue on. A second function is given by g of x. So remember, we can call our functions different things. Often we say f of x, but we can call them g of x, h of x, q of x, p of x. It's just a different name for a function. It's like y1, y2, y3. So a second function is given by g of x is equal to kp to the power of x minus 9, where p is greater than 0. The graph of y is equal to g of x intersects the x-axis at points a, which is 0, -5, and it passes through the points b, 3, 4, 5. So a lot going on here. It's pretty dense. What do we have? We have some function, and it's given by k times p to the power of x minus 9. And x is just our variable. Like, we can see g of x is equal to y, and that's exactly what they do here. So it's more or less like y is equal to k times p of x minus 9. And there are these things that we don't know. We don't know p, and we don't know k. But it's some kind of exponential function. And exponential functions, remember, are ones that look often like this, and they go off into infinity, or they start low and then they kind of decay and so on. That's what this is. An exponential function is when our variable x is in this is power, is as an exponent, essentially. Okay. So that's what we've got in this case. We've got some function. It's an exponential function. It's going to go off into infinity, or it's going to decay. And the question is, the first part of it is find the value of x and then find the value of p. Okay, so this one's kind of tricky. If we're looking at this function right here, y is equal to k times p of x minus 9, we have 1, 2, 3, 4 unknowns. And how can we solve for k? K is this value right here. It's kind of a tricky question, but they give us these 2 points, 0, -5, and 3, 4.5. This value right here, this 0, is going to be significant because it's a point when x is equal to 0 and y is equal to -5. And just like our linear equations, for example, when we have y is equal to mx plus b, if x itself is equal to 0, it also, in this case, it would take away our m value, and it would give us our y-intercept right away. And something special also happens when we're dealing with exponential functions. When x is equal to 0, we have p to the power of 0, and we know that anything to the power of 0 just becomes 1. So we have some function. We don't know these two values, this value of k, this value of p, but they did give us 2 points. What makes this kind of tricky, or at least so far as I see, as far as I think, it's not a straightforward input-output question. We have to decide. And you can kind of use process of elimination. If we have some unknowns and we have some given points, it's often the case that we're going to want to substitute some of these values. And in some sense, we could try this and then nothing would really happen. But when we try this value, we can get a result. So let's go ahead and substitute this value of a right here. Okay. So for a, we know that this is our x value and this is our y value. So let's substitute those values in. So for k, we have -5 is equal to k times p raised to the power of 0, and it's -9. We said earlier that p to the power of 0 was just 1. So now we have negative 5 is equal to k minus 9. And we can end solve this if you want, or just a little algebra, and we have k is equal to 4. Alright, so that's the first value of k. So, knowing that piece of information, let's actually put that into our function right here. So we have y is equal to, we know what k is now, we don't know what p is, px minus 9. Now we have some function with 1, 2, 3 unknowns, and we've got another point that we've never used. So in order to find this value of p, we can plug in a value of x and a value of y, and then that should allow us to find this unknown right here. So let's go ahead and work that out for part 2. Might need that space later, so let's just substitute. So here we have another xy value, or xy coordinate point. Let's substitute 4.5 equals 4. P we don't know. X is equal to 3 minus 9. And this one actually going to go ahead and, I don't know why that doesn't work. There we go. Going to go ahead and solve for p in this case. So let's go back to the calculator and work this out. Menu, algebra, numerical solve. 4.5 is equal to 4 times, let's say p to the 3 minus 9, and then ask the calculator to solve for p. Okay. In this case, p is equal to 1.5. So let's go back to the document. P is equal to 1.5. So kind of a tricky question, but potentially through elimination. Like when you're given an equation such as this, and you're asked to solve for an unknown, most often, not always, but most often, especially when they give you points, they're asking you to substitute into the equation to solve for the unknowns. What makes this one a little trickier is they give you 2 options, and order actually matters. So in this case, we need to substitute this 0, negative 5. 0 you can kind of remember as a special value, and it often helps clean things up, or in this case, eliminate a variable that we don't exactly want. And so, in this case, order matters. Substitute this, and then afterwards we can substitute the second value to find p. Alright, question F right here. Write down the equation of the horizontal asymptote of y equals g of x. So what are they talking about when they're talking about a horizontal asymptote? A horizontal asymptote is a line that we approach but never reach. So we looked earlier, we had that vertical asymptote all the way back here. This is our vertical asymptote, this line that we approach vertically but never reach. And that was at x is equal to 0, that vertical asymptote. A horizontal asymptote is a line that we approach and never reach. So if we have, let's say, typical example is a cooling cup of tea, and we have some exponential function, and then eventually this function is going to approach, or this teacup in this case, is going to approach but never really reach. I should do that a little lower, I suppose, but never going to reach this certain temperature, in this case like room temperature, for example. Another example would be if someone is jumping out of an airplane, parachuting, they would have, some 0 point of their initial speed, and then after a while they would reach what's called terminal velocity, and then again there would be some point that they would approach but never reach. This is what's called a horizontal asymptote. In this case, what is the horizontal asymptote of this function y is equal to g of x? What is the line that we approach and never reach? So here's our function. Y is equal to 4 times p of x minus 9. Oh, sorry, not p of x. We know p. So 4 times 1.5 multiplied by, raised to the power of x minus 9. Remember, order of operations. Don't be tempted to multiply 4 and 1.5 together and just write it as 6 to the x. That would not be correct. Order of operations, it's 1.5 raised to the power of x, then multiplied by 4, and then you take away 9. So don't simplify anything, just leave it as it is. That's our function. Okay. Horizontal asymptote. Generally, I mean, we can graph it to find out, but what can we say? What can we say? I don't want to go and give too lengthy of an explanation, but if we have this function right here, and we have certain x and y values, so here's x, here's y. When x is equal to 0, remember this goes away, and we'll have this right here. When x is equal to 0, this 1.5 will just become 1, and we'll have 4 minus 9, and this itself will equal -5. So that's a point we already had, 0, -5. And then we can ask, okay, well, when x gets bigger, when x becomes 2 or 3 or 10, we have 1.5, for example, raised to the power of 10, 1.5 multiplied by the power of 10. It's just getting bigger and bigger and bigger as x becomes larger. So 1.5 raised to the power of 10, 1.5 multiplied by itself 10 times, times 4, and then we just take away 9, which becomes less and less significant. So it gets bigger and bigger and bigger. In this case, our function will look something like this. So it starts low, and then it goes off into infinity. And then when x is less, when we go the other way in this case, well, what happens is x itself will become negative. And without going into too much detail, 1.5 to the negative x is just 1 over 1.5 to the x. So we're dividing 1 by some massive, massive number to the point where when we multiply that super, super small number by 4, the 4 kind of goes away and we're just left with this remainder, this -9. So it becomes very, very small. When we go this way, this becomes very, very large. But when it becomes very, very small, there's some value that doesn't go away, that's always by itself. This -9, it's not affected by what happens here with this x. It's just by itself, this -9. And so what does that mean? When x becomes very, very small, we reach some asymptote, some line that we approach but never reach. And in this case, it would be y is equal to -9. So write down the equation. The equation means we're asked for an equal sign. The equation of the horizontal asymptote. In this case, it's going to be this horizontal line. Remember, our horizontal lines are always in terms of y. Right? So this would be like y is equal to 4. Above here, we had this value of y is equal to 7. These are our horizontal lines, right? And our vertical lines are, in this case, x is equal to 0 or x is equal to 2. These are our vertical lines, and these are our horizontal lines. So if we want to write an equation, what is our horizontal asymptote? It's -9 in this case. I want to show you really quick how to potentially do this on a graphing calculator. So going back to the graphing calculator for a sec, let's put in our function 4 times 1.5 raised to the power of x minus 9. And so we've got this function, and if we, let's say, zoom out and just keep zooming out, I mean, right away we kind of already see, okay, what's this line that it's kind of settling on, this horizontal line. It seems to get flat. It doesn't go much beyond this point. In this case, we can just use graph trace. And graph trace will give us some kind of point, and we can just keep going to the left and left, or we could put in some massive value in some cases. But already here it looks like we're settled on this value of -9, and this is the value that we rest at in some sense. It never goes lower than this point, this y is equal to -9. And so, once again, you can solve it this way. What's our horizontal asymptote? Y is equal to -9. All right. Part G. Find the solution of f of x equals g of x when x is equal to 0. So this again, try not to be, the notation could potentially be intimidating. This f of x is equal to g of x. So what does this f of x equal to g of x mean? It means we have this one function and this other function in less kind of like maybe more intimidating function notation. It's like we've got an equation of y1 and y2. So when does y1 equal y2? So this is our g of x right here, and f of x was on the previous page. So what they're asking is, okay, well, we know one of the functions looks kind of like this, and they have this other function up here. When do they meet? When does the first function, f of x, equal the second function, g of x? When are they both equivalent? When do they both have the same value? And there's two ways we can solve this. We can either n-solve or work this out graphically. So let's n-solve this potentially first, and then we'll work it out graphically. So f of x, I've got to go find it right here. 3x minus 1 plus 4x to the negative 2. All right. 3x plus 1 minus 4, 4x to the negative 2 minus 4x to the negative 2, and this other function was, I believe, 4 times 1.5 to the power of x minus 9. There it is. Okay. And to be honest, if we just want to find out when does f of x equal g of x, we can just n-solve this equation and solve for x. Sometimes n-solve actually has some trouble with exponentials, but in this case, it's possible that it will work. We may need to graph it, but let's see if we can n-solve this first off. Okay. Menu, algebra, numerical solve. 3x plus 1 minus 4x to the negative 2 equals 4, and then I think it didn't really like that. 1.5 to the power of x minus 9, and we want to ask the calculator to solve for x. So it looks rather intimidating, but essentially we're saying, when does this one function, which we defined as this kind of rational equation, this rational function, when does this one function equal this other one? And it actually worked in this case. Okay. X. So we'll go back to the document and write this out. So the value that we have is equal to 0.7647. So we'll write 74671 and so on to 3 sig figs 765. Okay. Not bad. Graphically, I hope this isn't too long-winded, but I'll give a quick demonstration of what's happening graphically. This is one of our functions. This is g of x, right? This exponential function, which is going off into infinity. This is g of x. And then we had f of x, that original function. Remember, it went down like this, and then it had its minimum, and then it went across. And there was that point where, what did it look like? It looked something like this, actually, yeah. And then it had that vertical asymptote right here, and then it went off. Okay, so actually looking at this graphically, it looks like there might be two solutions, which might be something that n-solve might miss. Ah, I see. I'm sorry, this is my mistake in reading this. Find the solution of f of x when x is greater than 0. So although we might have two solutions, it's when x is greater than 0. So we're really just looking for this value right here. So let's go ahead and graph it, and we can look at this way to do it as well if you're more comfortable. Feel free to skip ahead if you're happy with the n-solve method. Okay, so here is the original function that we had. Actually, that's all right. 3x minus 1 plus 4x to the negative 2. That's our original function. Let's go menu, graph entry function. Let's put the second function in, which was 4 times 1.5 raised to the power of x minus 9. Okay, looks like we have our intersection right here, and this should give us the equation. So analyze graph, intersection, and in this case, it gives us a different value. 3x plus 1 minus 4x to the negative 2. 3x, I wrote 3x plus 1 on that original nsolve question, but it's actually 3x minus 1. So here we go. Let's write this out. I'm going to go back to the document and write this out tentatively as x is equal to 4. And I'm going to go ahead and type this quickly back into nsolve. Okay. Menu, algebra, numerical solve. And so we have 3x minus 1 minus 4x to the negative 2. And this should equal 4 times 1.5 raised to the power of x minus 9. Then we want to solve for x. Actually, just make sure that these are all correct. 3x minus 1 plus 4x. Okay, so maybe there's something to be said about an nsolve method. Plus 4x to the negative 2, and then going down further, 4 times 1.5 to the x minus 9. This looks good, and hopefully it gives a value of 4. Otherwise, I'm not sure. Geez. Okay, that's not terrible, actually. It's finding the closest value. So what nsolve is doing is it's finding the closest value to 0, and we know a value of 4 is actually further away. So taking this again, and then asking nsolve to solve for something, let's say, beyond 2, for example. What could we do? In this case, we want to solve for something greater than 2. I'm almost wondering whether nsolve is going to be an appropriate strategy. There is a way to ask nsolve to solve after a given point, but I'm not exactly remembering it here. I'm looking for this function where it says greater than. Not sure if we can say x is greater than 2. Let's see. X is greater than 2? No. Okay. X. Did we put comma 2 in here? There it is. Okay. So there we go. If you want nsolve to solve after a given value, normally nsolve will solve the closest value to 0. If we want nsolve to solve after a given point, or closest to, in this case, closest to some value, in this case we can put in larger and larger values. I believe what this case is, it asks you to solve something greater than 2. In this case it gave us that value of 4. Okay, not a bad learning experience. I apologize if it was a little drawn out. I guess maybe it shows that nsolve can have its risks, I guess. Okay, let's go on to question 3. So here we have a 15-mark question. Let's read it. The depth of water, W meters, in a particular harbor can be modeled by the function Wt equals A cos Bt plus D, where T is the length of time in minutes after 6 in the morning. So a few things going on. What is this function? The function maps the depth of water at a particular time. So essentially, even when we're dealing with cosine or sine or trigonometric functions in general, we're still dealing with inputs and outputs in some kind of sense. That is to say, we input some value of t, and then we get some value of the depth of water at this instance. Continue on. On January 20th, the first high tide occurs at 6 in the morning, at which time the depth of the water is 18 meters. The following low tide occurs at 12:15 when the depth of water is 4 meters. This is shown in the diagram. So a few things going on here. They're telling us time. Time is measured in minutes. This is our input. And time measured in minutes after 6 in the morning. So even though if we were to put in some value of t is equal to 0, this is actually corresponding to a value of 6 in the morning. And that's probably going to be important later on in the question. They're also giving us a high tide, a maximum at this point at 6 in the morning, which again would correspond to t is equal to 0, I suppose. And they're telling us that's 18 meters. And they're also giving us a low tide, 12:15, which is 4 meters. So they're giving us a max and a min in this instance as well. Okay, so we've got some trig function, and it's going to map onto some real-world situation where at the very end we should be able to input some value of t and then find the depth of water at that point. And these 4 questions, A, B, C, D here, they're asking us to find the value of A, value of D, the period of the function in minutes, and then the value of B. And if we know all of those variables, A, B, and D, then we should be able to create some function that maps onto this real-world situation. All right, so let's go ahead. I'm going to give a brief kind of explanation of trigonometric functions in general, and then we'll work through this problem, what these values of A, B, and D actually mean. What makes this problem, I think, particularly challenging, or trigonometric functions in general, is that there is nothing in the formula booklet in which to appeal to or kind of rely on in some sense. That is to say, the formula for the amplitude, or this midline, or this value of B, which is called the frequency, or even the period, this is something that we, in some sense, have to commit to memory, but the positive thing is that you can use intuition to work through a lot of these things. All right, so let's go and just have a quick overview of trig functions. I'm going to draw a set of axes, and let's draw it for this instance of weight as a function of, the depth of the water as a function of time, and they're telling us it's A cos B of t plus D. And this is the same thing, like if we wanted to, we could write it in general as y is equal to A cos B of x plus D. In this instance, t is just our variable, and then the depth of water is just our y value, our output. So either case, we'll use w and t for this function itself. Okay, so we have 2 functions. We don't ever, in the IB, they'll always give us the function. They'll always tell us it's a cosine or a sine function. The only difference between the two, I'll make another quick graph up here. The only difference between a cosine and a sine function is that a cosine begins at its highest point and then sweeps through a full cycle, whereas, and then I'll just complete a little more than a cycle, a sine function starts at its midpoint and then it goes through a cycle. Oops. Let me just edit that just a little. Sine function will go through its midpoint first, and then it will go through a cycle. So sine function starts here, cosine function starts here. So this would be cos of x, and then this would be y is equal to sine x. And the IB will always give you the cosine or a sine. In this case, we're starting from our maximum, so we've got a cosine here. Okay, so now what are these values? What are these values of A, B, and D here? A, B, and D. A corresponds to the amplitude, and let's write that out here. A is the amplitude. And what the amplitude tests is if we've got some function. I'm going to write a general cosine function here. If we've got some function, so it starts at its max, it's a cosine function, and then it goes down, and then it goes up again, and then it completes one full cycle. So amplitude measures the distance that we are from the midline. So if this is our midline or our resting point, the average value, amplitude measures the distance from the midline to the highest point. And to find the amplitude, we can take the max, the maximum, I'm just actually going to write max, minus the minimum, and then we can divide by 2. So max minus min, if we want to find the distance from the highest point to the lowest point, we could take the maximum minus the minimum and then divide by 2. So if we imagine this is the maximum, we want to see the distance that we travel from the highest to the lowest point. This would of course give us 2a, but we don't want 2a, we just want a. So amplitude max minus min over 2. And that's what this value of a corresponds to. This value of d is the midline, or what we're shifting our function up or down by. So for example, if we didn't want our function to be at this midline right here, we could define a midline up here, for example. And then the midline of this function would be something like this, I suppose. So it would be shifted up. And that's exactly what our midline would do, and then it would go over. And so our midline would now rest something around here, I suppose, or maybe a little higher. This would be the value of the midline, or the center line. And if this midline is the point at which we rest at, or the center point, to find the value of d, which we'll call the midline, is just going to be max plus min over 2. Essentially the center line that you run through, or that our trig function runs through. So max plus min gives you the value of d. Maybe I'll write these out. So this is a, this is amplitude, this is d, this is the midline. And then later on, they asked for the period. The period is the time taken for one complete cycle. So I'm actually going to write that out. The period. The period is not something that's given to us again in the formula booklet. It's the time taken for one whole or one complete cycle. So to do this, we often need to look at the graph, or sometimes they'll give us some information. In this case, they actually do give us some information here. But oftentimes we would choose one point on the graph and then ask ourselves the question, when has this graph swept through, or when has this function swept through one complete cycle? And we see that, okay, it gets back to its max point right here, and then how long does this take? That would be our period, the time taken for one complete cycle. And that would be the period. This last value, which is probably the most challenging to solve for, this value of b, this is called the frequency. And this is probably the more complicated one to solve. Our formula for frequency, or b, is equal to 360 divided by 360 divided by the period, the time taken to complete one cycle. Why is it 360 degrees? It has to do with what's called the unit circle. We won't go into depth on this, but it's potentially enough to know that we sweep through one whole circle in 360 degrees, and we're asking essentially how many periods fit into 360 degrees. And that will give us our value of b. So a, once again, our amplitude, the distance from the midline to the highest point. And how can we find that? Let's find that distance, the maximum minus the minimum, and then divide by 2. So max minus min, divide by 2. If you know the midline itself, sometimes you can find the midline first. That one might be the easiest one to find. That's just our kind of line that we rest at. So that would be max plus min over 2, or essentially the average, right? So here's the highest point, here's the lowest point. What's that midline? What's the line that goes right through the center? And then if you know the midline, if you find the midline, you can find the distance from the midline to the max, and that's exactly what the amplitude is as well. So you can reverse the process, find d, and then say, okay, well, if this is the midline, how much do we need to go up by or down by to get to our max from the midline, or to the min from the midline? That would also be another way to find it, the value of a, or the amplitude. Here they structure it a little differently, but if you can find D, then it's often easy to find A as well. Period is the time taken for one complete cycle once again. So how long does it take us to go from one point to another corresponding point, or how long do we complete a full cycle? And frequency, this has to do with the unit circle, which is maybe a little complex in terms of its theory potentially, but the question we're essentially asking is, how many cycles can we fit into 360 degrees? And this is going to give us the value of B. All right, so once again, none of this is in the formula booklet. None of these formulas are in the formula booklet. We kind of have to remember what they are. D, the midline. A, the distance from the midline to its maximum point. Period, time taken for one cycle. And then frequency, probably the most challenging of all, how many periods, how many cycles fit into 360 degrees. All right. So now that we've got that out of the way, I suppose, let's see if we can apply this to this question right here. All right, so they want us to find the value of A. I'm actually going to work it out in reverse order because I think that might actually be helpful. I'm going to find D first and then A. So D, we said, was the midline. Let's even maybe use the same colors here. So this was D, this was the midline, and that's D is equal to max plus min divided by 2. So in this case, maximum, they told us the water had its maximum depth at 18 and its low tide at 4 meters. So once again, max at 18, minimum at 4. So if we have our midline, that center line that we go through, the average, it's going to be 18 plus 4 over 2, or 22 over 2, or 11. And that would be our value of 2. So let's box that in and say D is equal to 11. Okay. So now, if we wanted to, I mean, like through intuition, we could find the value of amplitude in another way. So if we know the midline is equal to 11, maybe even draw it in here, I suppose, we can then ask ourselves the question, okay, well, if this is 18 and our midline is 11, then what distance do we need to go from, let's say, the midline to the highest point? Or similarly, if we know this is equal to 4 and our midline is at 11 right here, what distance do we need to travel? And once again, it's 7. So sometimes it is actually helpful to go from D and then to A, or D into A. Either way, let's work it out. We found the value of 7 just through intuition. This is a 2-mark question, so they are expecting some process. You could probably write, and I imagine you could write 11 plus what is equal to 18, or 18 minus 11, and this would give you 7. But let's use our formula right here for amplitude. That's what A is. Amplitude. A is equal to max minus min. So the distance from the peak to the trough, the highest point to the lowest point, divide by 2. And now we have 18 minus 4 over 2, or 14 over 2. And this gives us a value of 7. So we know that A is equal to 7 here. Okay, the period of the function. Let's ask ourselves the question, okay, how long does it take to go through one complete cycle? This one's actually a little more challenging. We can see it's even 3 marks. So there's going to be some extra kind of computation involved, something extra in terms of the process. So let's ask ourselves the question. Going to need a little more space. I'm going to write it up here. The period, the time taken to go from one complete cycle. So we know we have a high tide, which occurs at 6 in the morning. So right here, this is 6 in the morning. Here it is as well, 6 in the morning. And then all the way here, we have our low tide. And I'm going to erase some of this, I suppose. All right, all the way here, we have our low tide, which it's hard to tell on the graph, and that's probably purposeful, I suppose. Low tide occurs at 12:15, and here it's in minutes, so we're going to need to do some conversion. But we know a max, we know when it occurs, and we know where the min occurs. And when we go from a max to a min, you can ask yourself, okay, well, how many cycles have we gone through? If we've gone from the max to the min, we've gone through half a cycle, and we're going to need to go from the min to the max again, and that's going to be one other half cycle. So essentially what we have here, I hope this isn't too kind of lengthy, but we have this instance where we know, let's say I'm going to draw a standard function. We know we've gone from our max to our min, and now the question is, okay, well, if we know that this itself is one half cycle, it's going to be another half cycle until we go one full cycle. So let's ask that question. So from 6 to 12:15, how many minutes have passed, or how much time has passed? So let's see the distance. This is going to be a little funny. I think it's actually best to use intuition. If you started at 6 in the morning and then you go all the way to 12:15, how many hours pass? Well, if you start at 6 and you go to 12:15, we have 6 hours and 15 minutes. 16 hours and 15 minutes. But of course, the function won't really take hours and minutes, two different kinds of units. T itself is just in terms of minutes, and that's what they're asking us to find the period. They're asking us to find the period in terms of minutes. So 6 hours, we know there's 60 minutes in an hour, so this is going to be 60 times, 6 times 60. So 6 times 60 is going to be 360 minutes. I'm going to write that out. 360 minutes. Let's just write 360. And then we also have this 15 minutes right here. So what do we know? We know we go through a half cycle in 360 plus 15. 360 plus 15 is going to equal 375. So we go through a half cycle in 375 minutes. Let me just make sure that's all correct. 6 hours plus 15. 6 times 60 is 360 plus 15, 375. Okay, so half cycle in 375. How much is a full cycle? Well, we'll just multiply by 2. Multiply by 2. And 375 times 2 will give us 750 minutes. Okay, so once again, from 6 in the morning to 12:15, we go 6 hours and 15 minutes. 6 hours, there's 60 minutes in every single hour. 6 times 6, 36, plus this 15 minutes. 375 minutes to go a half cycle, therefore a full cycle is 750. So let's say the period is equal to 750 minutes. So the calculations themselves, we can see they're not like super challenging themselves. Essentially it's really knowing where to find the information, max and min, max plus min over 2, and these kind of things. Period, time taken for a full cycle. But this is otherwise somewhat of a challenging question, at least to get started in some sense. So find the value of b. B itself is the frequency. B is, let's use the same color once again. The formula for b is equal to 360 over the period. This is probably the trickiest one to remember. So 360 over the time taken for one complete cycle, 750, and I'm going to work that out and we'll get a decimal of 0.48. Okay, so we know that b is equal to 0.48. Really, once you become familiar with this, this is a great 9 marks. And once you're familiar with trig functions, and they do often have a real similar kind of structure, especially when the graph is given to you, that potentially it's a good way to maximize results and so. Okay, so now we know A, B, and D, so we know everything there is about this function, and we should be able to map onto this situation. Usually after this, they ask us to apply it. Now that we've got the function, let's do something with it. Okay, so what do we have here? Naomi is sailing to the harbor on the morning of 20th of January. Boats can enter or leave the harbor only when the depth of water is at least 6 meters. Find the latest time before 12 to the nearest minute that Naomi can enter the harbor. Okay, so let's work this out. We're going to need to graph this one. Let's go ahead and, running out of space a little, but let's write out our function itself. So we have y is equal to a cos b of t plus d. A we found out was 7. 7 cos b we said was 0.48, t plus, and then the midline again was equal to 11. So this is our function, 7 cos 0.48 t plus 11. And if we put that into the calculator, we should be able to graphically see what's going on here. Okay, so she's sailing into the harbor on the 20th of January, that's the day. Boats can enter or leave the harbor only when the depth of water is at least 6 meters. So only when the depth of water is at least 6 meters. So let's erase this, and let's see what this means. So this function tracks the depth of water through time. Boats can enter the harbor only when the depth is at least 6 meters. So this is 6 meters right here. This is our W, right? W is equal to 6. That's our output essentially. W is equal to 6, and where can she enter the harbor? Well, she can enter the harbor here and here and here. The depth is at least 6, right? At least 6. It's above this line, right? But after this time rather, now the water is less than 6 meters, so she can no longer go into the harbor. So really, what we would like to do is find the point at which the water goes from being above 6 meters to now below 6 meters. That's going to be the last time she can enter into the harbor. Okay, so let's go ahead and look at the calculator here. Here we go. So I'll just bring a new window up. Make sure you're in degrees when you are graphing this as well. Sometimes there's a difference between the calculator window and the graphing window itself. So make sure that this is in degrees. Otherwise you'll get some, well, you're getting correct results. 7 cos 0.48x plus 11. So the calculator only takes x's, of course. All right. And for trig functions, these can potentially be a little difficult to find the window of. Zoom fit won't work too well. This is definitely not a quadratic or anything like that. And if we zoom out, it won't give us all that great of an idea of what's going on. So when we're doing or working with trig functions, I recommend you go to the window settings and get some custom windows. And this is x min, x max, minimum x max x values, and then min max for y. So what do we know? We know that we're starting off when t is equal to 0, so let's put in maybe like t is equal to 10, for example. Max, we want to make sure we get at least one full cycle. We know a cycle is 750, so let's do 1,000 minutes. Scale is auto, that's fine. Y min, so the lowest point, the lowest depth was 4. Let's put 0 in just to get some buffer. We could even put -2 or something like that. And then the max depth was 18 meters. Let's put maybe 24. Let's actually put -2 just to get some buffer. Sometimes it's easier if you have a little cushion on either side. So from -10 minutes to 1,000 minutes, and then from a depth of -2 to 24. This will give us one full cycle, and it's much easier to work with now. Okay, so there's our function. Let's ask the question, when is this function equal to, or when is the depth of water equal to 6 meters? So there we go. So here's depth of water on the y-axis, time, and here's the depth of water through time. Question is, when is the depth equal to 6? So menu, analyze graph. Let's find the intersection. And here we go, 282.47. All right, so after 282 minutes and 47th of a minute, not 47 seconds, but 47th of a minute, that's when the water first becomes, reaches a depth of 6 meters, and then it's going to fall below that. Okay, so let's go ahead and go back to the document for a sec. I'm going to clear up some space here, just get rid of this, and then we'll write in here. Okay, and I think I'm going to get rid of this actually as well. I don't think we need this anymore. Okay, so what do we know? We know that this point right here is equal to 282.47, 282 minutes and 47th of a minute, and that's when we're at 6. This is our W or our Y value. We're at a depth of 6, and this is T, of course. Find the last time before 12 to the nearest minute that Naomi can enter the harbor. In this case, the last time before 12 to the nearest minute that Naomi can enter the harbor. Alright, so remember 12 o'clock would be 6 hours later, or 360 minutes later. This is 12 o'clock. The last time before 12 o'clock is right here. So 282 minutes. 282 minutes. Yeah, I think we would of course have to round down, even if it was 200 and let's say 82.8 minutes or something like that. If the IB wanted to trick you, we would still need to round down to 282, because at 283 minutes, it's now below 6 meters. So find the latest time before 12 to the nearest minute that Naomi can enter the harbor. 282 minutes. And let's actually show some process. Essentially, we would put 6, that's our output for the depth. 6 is equal to, and then our function. We want to know when is 6 equal to 7 cos 0.48 t plus 11. There it is. Plus 11. Essentially, we're asking for what value of t is the depth equal to 6. You might be wondering, yeah, can you end solve this? Potentially. In this case, you actually would be able to, but sometimes with end solve, graphing is better visual. Sometimes for trig functions in general, you might have a value that's after. Maybe that's the one we're looking for. Or end solve might give you something to the left, which won't be relevant. Graphing is going to be the easiest, I think. And then, of course, our answer is 282.47, or 282 minutes to the nearest minute. All right. Find the length of time in minutes between 6 in the morning and 3 o'clock on 20th of January, during which Naomi cannot enter or leave the harbor. So the length of time in minutes between 6 and 15 where she cannot enter or leave the harbor. So let's convert these to time first, just to get a better idea. This corresponds to t is equal to 0. And here, the distance from 6 to 15 is going to be 9 hours. So 9 hours times 60 minutes. You can put that in the calculator. That's going to correspond to a value of 540. So when t is equal to 540. And really, that doesn't seem too bad of a question. So when can she not enter or leave the harbor? Here she can enter or leave the harbor. Here she can enter or leave, as long as it's above 6. But from here to here, she cannot enter or leave. So we know one value. We know after 282 minutes, she cannot enter or leave. And then if we find this other value, then we'll find out the total time in which she cannot enter or leave. So this is her no entry, essentially. This is where you can't enter or leave. The water's too low. So not a bad 2-mark question. Let's go back to the calculator and find the other intersection point, essentially. Analyze graph, intersection, and we see that it is 467.53. So the total length of time, and we want to put this in minutes once again. So let's go ahead and find out, let's go back to the calculator. We know the first time in which she can't enter, and the distance between these 2 points is going to be the total length of time she can't enter. After this, it's okay to go in and out. So going back to the document for a sec, at 467.53 minus 282.47. So between these times, she cannot enter. So what is the total length of time between these 2 points? I'm going to work this out on the calculator that I have beside me. 467.53 minus 282.47. And this is 185 minutes. And what is this? This is a 6/100th of a minute. So find the length of time in minutes between 6 and 15 hours where she cannot enter. Okay, last little bit. Let's round this down to 185 minutes. And then let's convert this to, actually it's already in minutes. We don't need to convert it to anything. So that's it. That one wasn't too bad, actually. A 2-mark question. I don't know why this one was so challenging of a 4-mark question. But, okay. Find the latest time before 12 to the nearest minute that Naomi cannot enter the harbor. I see what they're asking now. Okay. So sometimes it's very rare. I mean, it's not often the case that the IB will make a mistake. Very, very rare things will be overly generous. When you see this 4 marks, it's possible to think of, okay, if you imagine the mark scheme itself, what are the steps that they're looking for? Here we need to graph it, of course. We need to set it equal to some value, and then we need to round this down to minutes. But they're asking for the latest time, not the total time that has passed. So 282 minutes. So just to go back to E here, this is all good right here, but E we need to do a little more work on. 282 minutes have passed. We know 6 in the morning is where we start, right here. So in a real world context, it wouldn't be enough to tell Naomi, for example, 282 minutes later, after 6, that's when you can't enter the harbor anymore. It would be more relevant in a real world context to tell what time exactly, what specific time. So in this case, we have to convert these minutes into hours and then find out the time, the latest time in which she can no longer enter. And that's something, to be honest, at first read that I myself missed. But 4 marks, that is a good indication. Okay, so 282 minutes. Let's divide this by 60 minutes. We know there are 60 minutes in 1 hour, so let's find out how many hours. I'm going to go ahead and do this on the calculator that I have beside me. And it's going to give us 4.7. So it's going to give us 4.7 hours. But that's not quite enough. That's, if we write this as 4.7 hours, it's 4 hours. And this 0.7 corresponds to 7/10, right? And 7/10 of an hour. Or let's just write 0.7 hours. 4 hours plus 0.7 hours. And how many total hours after 6 in the morning is this? 0.7 hours. 4 hours can stay as it is, but 0.7 hours in minutes we would need to multiply by 60, for example. And so 0.7 times 60 would give us 42. So what do we have? We have 4 hours, and then 0.7 hours, or 7/10 of an hour. 0.7 times 60, 60 minutes in an hour gives us 42 minutes. So 4 hours and 42 minutes. If we start at 6 in the morning and we go 4 hours and 42 minutes, 6 hours plus 4 hours gives us 10, and then 10:42. That would be the latest time that Naomi can enter. Sorry about that, I had missed that on first read. So depth of water, find the intersection point. It occurs at 282 minutes, but we're asked for the latest time before 12. And so 282 minutes, how many hours does that correspond to? Divide by 60. It corresponds to 4.7 hours. 4.7 hours is 4 hours and, well, 0.7 hours. 0.7 hours is, again, we don't want hours, we want it in, let's say, this minutes, not 70 minutes or anything like that. 7/10 of an hour, 42 minutes. 4 hours, 42 minutes, and then add that on to our starting value. So 6 plus 4 is 10, and then 42 minutes after. So 10:42. All right. Pretty good question overall. Apologies for the, not exactly the misread, but the oversight, I suppose. Okay. Let's go on question 4, to question 4. All right. 17-mark question. A large international sports tournament tests their athletes for banned substances. They interpret a positive test result as meaning that the athlete uses banned substances. A negative result means that they do not. The probability that an athlete uses banned substances is estimated to be 0.06. If an athlete uses banned substances, the probability that they will test positive is 0.71. If an athlete does not use banned substances, the probability that they will test negative is 0.98. So positive means that the athlete uses banned substances or they test positive. And negative means that they don't. Okay. Using the information given, copy into your answer booklet and complete the following tree diagram. So remember, this is a paper 2 question. They're bolding this just to remind you. It's not enough to simply write this out in the actual the test paper itself. You need to write this out in your answer booklet. So just make sure that that you do that. Okay. So let's work through this tree diagram right here. Remember, each of these are binary events. They either use banned substances or do not. One of these things has to happen, so the probability has to sum to 1. 100% of the people are either going to use or not use banned substances. So if this is 0.06, this must be 0.94. So they must add to 1 once again. Uses banned substances, this is right here along this branch, and then we'll go 0.71, and we know again these have to add to 1, so this should be 0.29. And then for this last part up here at the top, we'll need to use the information that they give us. So does not use banned substances. If an athlete does not use banned substances, the probability that they will test negative is 0.98. So 0.98. If they do not use banned substances, test negative, 0.98. But we do get some false positives. And there it is, 0.02. So all of these need to sum to 1. Okay, not a bad start. Part B, number 1. Determine the probability that a randomly selected athlete does not use banned substances and tests negative. Okay, so B1. So the athlete does not use banned substances and tests negative. So and let's just multiply along the branches in this case. So does not use banned substances and they test negative. So in this case, it's going to be 0.94 times 0.98. And I'm going to work that out just in the calculator that I have beside me. And this is I'm going to write it a little lower actually. So 0.94 times 0.98 equals 0.9212, or to 3 sig figs, 921. Okay. Randomly selected athlete does not use banned substances and test negative. Okay. And let's go to the second part of this question. If 2 athletes are selected at random, calculate the probability that both athletes do not use banned substances and both test negative. Okay. So in this case, whenever we say 2 athletes, you might want to think if it's dependent, as if, let's say, there are 100 athletes gathered into a room and we look for 2 athletes, and in that case, the denominator would change. For example, in this case, it would be, well, 94 out of 100 times 93 out of 99, something like that, a dependent event where the probability of something coming after depends on what came before. In this case, we don't actually have that situation. We just have a general statement of the, what can we say, the accuracy of these tests. So if 2 athletes are selected at random, probability that both athletes do not use banned substances and both test negative. So we know it's 0.921 probability, or roughly 92.1% chance that an athlete does not use banned substances and test negative. So 2 athletes selected at random, probability that both athletes, in this case it's just going to be the probability that the first athlete is one that does not use banned substances and test negative. That's 92% of our population, 92.1% of our population. And if we were to go out and select another individual and ask, well, how often does this occur? Well, again, that would be 92%. So 0.921 times 0.921. And I'm going to work that out here. 0.921. And this is going to give us 0.848241, or 0.848. Okay. All right. So just to summarize once again, 92%, the probability that someone doesn't use a banned substance and test negative is 92.1%. If we were to look at 2 people and ask, okay, how likely is that to happen to 2 people that were chosen? Well, the probability that the first person does not use banned substances and test negative is, well, 92.1%, and then the exact same thing the second time. So we're just multiplying across. All right, part C. Calculate the probability that a randomly selected athlete will receive an incorrect result. Okay, so an incorrect result. Let's see. Let's find out what that would be. So if they were to get an incorrect result, there are a few different ways that could happen. You could not use banned substances and test negative. That's one way. Oops, sorry, I think I deleted something. There we go. And test negative. And actually we can keep that here. It was 0.9, what was it? 0.921 something. 0.94 times 0.98, sorry. 0.9212. Or someone can use banned substances and test negative. So they can essentially cheat the system and be seen as clean. And that happens for, well, the 6% that use banned substances, 29% of those are caught. So we take 0.06 and we multiply by 0.29. And I'm going to work that on the calculator that I have beside me again. 0.06 times 0.29. So 29% of these 6%, and that would give us 0.0174. So roughly 1.74% of the population, I guess. Okay, so calculate the probability that a randomly selected athlete will receive an incorrect result. Well, what can we say? Okay. Whoops, sorry, I made a mistake. Does not use banned substances and tests positive. Here we go. That seemed a little high. Does not use banned substances, and you are tested and found to actually, after the results, it seems like you do actually use banned substances. So it'd be 0.94 times 0.02, 2% of the 94% of individuals. 188. Okay. So these people do not use, but they test positive, and these people use and they test negative. And these are the ways that we can get an incorrect result. So 0.0188 plus 0.0174. So I'll work it out here, I suppose. C1. So that would be 0.0188 plus 0.0174. 0.174. This would be the total number of people that take part in these tests and receive an incorrect result. What do we have? We have 0.0362. Or if we wanted to write this as a percent, 3.62%. IB is fine with fraction, decimal, or percent on probability. Okay, so, sorry that one was a little longer, but idea is this person's clean, but they tested dirty. This person is, I guess they're using substances, and then they test clean. So adding these two values, these are the two ways that someone can get an incorrect result. All right. And often on a paper too, this kind of transitions. Just reading the first part of this, it looks like it's a binomial. A random sample of 1,300 adults or athletes at the tournament are selected for testing. Calculate the expected number of athletes in the sample that will receive an incorrect result. Actually, this isn't a binomial. The next one looks like a binomial. C2. So this expected value is in our formula booklet, but expected value we can kind of think of through intuition as well. Expected number of athletes. Let's write this out. Expected number of athletes. What can we say? Roughly 3.62% receive a incorrect result. And if there's 1,300 people being tested, we would expect 3.62% of that 300 to receive an incorrect result. So let's take that value, 0.0362. This is that 3.62% times 1,300. And let's work that out. I'm going to work it out on the calculator that I have here. 362 times 1,300. 1,300, and this would give us 47.06 or 47 athletes. Okay. Expected number of athletes looks good. Okay. For expected value, actually, unless they ask us to round to the nearest athlete, we would generally put to 3 sig figs, just looking at here, they don't ask us to round to the nearest. So 47.1, I just have the mark scheme actually in front of me, and it does have as a final answer 47.1, but in brackets it says accept the too significant value of 47 for a final answer. So both are actually okay in this case, according to the mark scheme, but 47.1 is probably more common, as in right to 3 sig figs for expected value, even though it's a fractional amount. Okay, there we go. Here's the formula, if you want. Equals n times p. This is essentially number of trials times probability, or that 0.032 times 1300. So this is the number of trials, number of individuals, probability of occurrence. All right. Let's go on to part D. Team X are competing in the tournament. There are 20 athletes in this team. It is known that none of the athletes in Team X used banned substances. And then I suppose a sufficiently kind of cynical person would say that Team X is very good at hiding it. All right. Calculate the probability that none of the athletes in Team X will test positive. So it's known that none of the athletes use banned substances. Okay. So that means that does not use banned substances. They belong to this group right here. Calculate the probability that none of the athletes in Team X will test positive. So they're within this group that do not use banned substances. What's the chance? Probability that none of the athletes in Team X will test positive. So none that will test positive. So let's put test positive as a success. So this is a binomial question. We have a set number of trials. We have a probability of success, which is constant across trials, and the events themselves are independent of one another. That is to say, one person testing positive doesn't influence the chance of someone else testing negative or positive. So set number of trials, probability of success remains constant, and it's also binomial, as in there's either a success or failure. I might wait for this just to pass. All right. So let's call test positive a success, and this is number of successes. Number of successes. So if we're dealing with a binomial, we have number of trials, we have number of successes. We're going to have to define our success, number of successes, and then we also have probability of success. So in this case, we have number of trials is equal to 20. Number of successes, the probability that none of the athletes in Team X will test positive. We don't want any successes. And the probability that none of them will test positive. What is the probability of testing positive? Is 0.02. 0.02. So this looks like it should be quite small. Quite small, I think. So let's work this out, and actually we'll go into the calculator to try to solve this. Okay, so calculator, menu, probability, distributions, and we'll use binomial CDF. Number of trials, we have 20 athletes. The probability that someone tests positive, so they are not using banned substances, and the probability that they test positive is 0.02, and we want 0 successes. Whoops. We want 0 lower bound and 0 upper bound. That means we don't want any range. We just want 0 successes. And let's find that out. Okay. 0.667. So 0.667608. So roughly 66.8% chance that, even though all of them are clean, there's about 2/3 chance that everyone will come away with a clean test. Some of them might get a false positive. So let's go back to the document and write that in. So binom CDF, and we have 20 trials, probability of success 0, 0, and the result of that is equal to 0.667608 or 0.668. Okay. Yeah, I think that's okay. Let's see. I think there's actually another way to possibly do this. So test positive is equal to 0.02. Let's just use binomial, I suppose, in this case. I think that's going to be the most straightforward. And it'll set us up for this one as well, I think. So let's do question E. Determine the probability that more than 2 athletes in Team X will test positive. So more than 2 athletes in the team will test positive. So this is still these individuals that do not use banned substances. This is the probability of success. I mean, it's not exactly a success to test positive, in this case at least. In most cases, generally. But we can define success. Success is, you can kind of think of it as probability of occurrence. Okay. So let's go ahead. We can use a binomial distribution once again. So number of trials, number of successes, which I guess you can kind of think about this as occurrences, and then probability of success. The only thing that is going to change in this one, we'll still have 20 trials. The probability of testing positive, given that you have not taken any banned substances, is still 2% or 0.02. The number of successes, in this case we have a range. We want a probability that more than 2 athletes. Binomial can be tricky, and to be honest, I'm glad I read this a second time. It's more than 2. So 0 athletes, no. 1 athlete, no. 2 athletes is still no. We want more than 2 athletes. So in this case, anything from 3 to 20 athletes. What's the probability that between 3 and 20 athletes test positive? So let's go ahead and go back to the calculator. So menu, probability, distributions, binomial CDF, 20 athletes once again, chance of testing positive 0.02. What's the chance that between 3 and 20 athletes test positive? In this case, a rather small number. Looks like 0.007069. So let's go back to the document and write this out. What did we perform? Binomial CDF, 20 trials, probability of success, and the range is from 3 to 20. And the result was 0.0070, so that looks like a 6, 0.007069. To 3 sig figs. Remember, a significant figure only begins after a significant digit. So this is 1, 2, 3, and so. Okay, so 0.00707. There we go. Okay. Not a bad question. All right, final question on paper 2. Should be a good challenge. Let's have a look. Maximum mark is 17. A large closed container in the shape of a half cylinder with a rectangular lid is to be constructed with a volume of 0.8 meters cubed. The container has a length of L meters and a radius of R meters. Part A asks us to find an exact expression for L in terms of R and pi. So we want to write L in terms of two other, one is a variable and one is a constant. So in terms of r and pi. So whenever we say in terms of, it means that we are having L on one side, and then we'll have r and pi on the other. And maybe r and pi will be multiplied by something or divided by something, but we want L on one side, and we want to write L in terms of r and pi in some kind of combination. Maybe we're going to square one, divide one, so on, so on, so on. All right, so find an expression for L in terms of r and pi. So let's see how these things are related. What do we know? What do we know? What do we know? The only value that they really give us is the volume, and it's equal to 0.8 meters cubed. Okay, and this pi should indicate that we're going to be dealing with something with circles. So if we want to write in terms of r and pi, how could we write this out? What do we have? We have a cylinder, but really only a half cylinder. So let's go into the formula booklet and find the formula for the volume of a cylinder. Okay, so here we are. Here's our formula booklet. This is going to be in geometry and trigonometry. And let's find the volume of a cylinder right here. And it's equal to pi r squared times height. R is the radius, h is the height. Okay. Pi r squared times height, that's the volume of a cylinder. Okay, so we know that the volume is equal to pi r squared times height, but we don't have the volume of a whole cylinder here. We just have half of a cylinder. So we can write v half, but I'm going to write it just in terms of what we have here. So our volume itself is equal to 0.8. So we know that the volume of this whole cylinder is going to be equal to 0.8. And as an expression, it's going to be pi r squared times h, but we only have half of a cylinder. So that's going to be our volume of a, let's say a half cylinder, this v sub h, volume of a half cylinder. And what is the volume of our half cylinder? It's equal to 0.8. So let's write that out. 0.8 is equal to pi r squared times h over 2. You might say, okay, well, how does that get us closer to this L, finding this L? When we work this out, when we use this volume of a cylinder formula, we had this h here. But remember, if we're talking about the volume of a cylinder, let's draw a cylinder here, for example. The volume is going to be given by pi r squared, or area of the base, this is r right here, times h. And all we've done for this cylinder is we've laid it on its side, and we've cut it in half. So the distance from the bottom to the top of the cylinder, sure, when it's on its base right here, it's the height. But if we lay it on its side, then now this becomes the length. So the height of the cylinder essentially is L. So let's go ahead and write that in. Okay. So really it's pi r times L times L times L. Okay. Whoops, I gotta get rid of that. Alright. So now find an exact expression for L in terms of r and pi. And this is actually going to be a fair bit of algebra, actually. More than you might expect, potentially, on an AI paper. So we don't want this 2 here. This is pi r squared divided by 2, but we don't want pi r squared times L divided by 2. We want L all by itself. So how can we do that? Let's get rid of this divide by 2, and to do that, let's multiply both sides by 2. So we're multiplying both sides by 2. 2 divided by 2 equals 1, so they kind of cancel out. They do cancel out. And now we have 1.6 is equal to pi r squared times L. Remember, pi r squared is just the area of the base. The volume is area of the base. This is area of the base times height, which when we have the cylinder on its side, this is just our height. And now the last step to get L all by itself, what do we have? We now have L being multiplied by pi r squared. So to get rid of this pi r squared, we don't want it multiplied, we divide both sides by pi r squared. Pi r squared. And now, again, pi r squared divided by pi r squared, anything divided by itself is just equal to 1. So this pi r squared just equals 1. And now we have L is equal to 1.6 over pi r squared, or L is equal to 1.6 over pi r squared as we would read it. Okay, so that is, to be honest, quite a challenging question, especially for a 2-mark question, and a significant amount of actually algebra. Okay, so there it is. L is equal to 1.6 pi r squared. We have an expression for L in terms of r and pi. So L's on one side, and pi and r are on the other. Okay. So remember, I guess now the time would be to say paper 2 questions, especially something like this, 17 marks. Look for the entry points. This is an admittedly, quite challenging question involving a fair bit of algebraic manipulation. The mark scheme awards a mark for setting up this 0.8 times pi r squared times L. So just working with the volume of a cylinder, recognizing that L, or the height rather, corresponds to the length in this case because it's on its side. This would give you 1 out of the 2 marks. So potentially not too bad. Algebraic manipulation is challenging. Essentially we want to use opposite operations. So if we're dividing by 2, we see this, everything is divided by 2. We want to multiply by 2. If we're multiplying by pi r squared, we want to do the opposite and divide both sides by pi r squared. End goal is to get this variable, this L, all by itself. Okay, let's move on. The container will be constructed using 2 different materials. The material for both the curved surface and the rectangular lid of the container costs $4.40 per square meter. The material for the semicircular ends costs $P per square meter. Okay. So, let's see. The container will be constructed using 2 different materials, curved surface and the rectangular lid. So what is the curved surface and the rectangular lid? The curved surface is, of course, this right here. And the rectangular lid is this. That doesn't show up too well, but there it is. I'll write it here as well. It's a little better. So this is the rectangular lid right here. I hope that's coming through okay. That's a little better. And then, of course, the curved surface along the edge. I hope you can see that. Yeah, that's fine. And this is going to be $4.40 per square meter. And the semicircular ends, that's these right here. This costs P dollars per square meter. We don't know yet. So I'm actually going to write this out in a different color just to make it a little more visible. These are the curved surface and the rectangular lid. Okay. All right. The cost C of the materials to construct the container can be written in terms of R and P. So again, we have this in terms of R and P, where P is greater than 0 and R is greater than 0. So what does that mean? Radius is greater than 0, and P, the price, is as well greater than 0. Okay. Show that the cost is equal to 7.04 r to the negative 1, 14.08 over pi times r to the negative 1, and then p pi r squared. You might say, geez, that's very intimidating. You know, how do we go about this? Well, actually, we'll work this out. But remember, things are compartmentalized. We have a 3-mark question right after, which is just asking you to derive this, and we already have our exponents as a negative 1. So remember this, jumping ahead a little, this 1 over x, we wrote as x to the negative 1 because it's not possible to derive this as it is. We first need to convert it to this form where we get our exponents, a negative exponent. No variables in the denominator allowed. We've already got this converted. So this is a nice kind of, you know, generous question. Not generous, but it's very manageable. So remember that the questions themselves on a paper 2 are somewhat compartmentalized. All right. So show that c is equal to 7.04 r to the negative 1, and so on, so on. What does this r to the negative 1 mean? It means 1 over r. So we can go both ways in this case. R to the negative 2 is equal to 1 over r squared. And if we get something like 1 over r cubed, this is equal to r to the negative 3, and so on, so on, so on. That's what that r to the negative 1 means. Okay. So let's try to work this out. Need some good space. Here's B. Okay. So what do we know? Cost is 440 per square meter, and that's for the curved surface and the rectangular lid. So let's write out cost equals, and then let's write it out in terms of curved surface plus rectangular lid, that's all going to be equal to 440 per square meter. So curved surface times rectangular lid times 440. So if we know the area of this, we can multiply it by 440. And it's also going to be equal to, and we've got a half semicircle right here, and these are our, let's just call it semicircular ends. I'm going to write S circular ends, and if we find the area of that, then we can multiply it by P, and that should give us our cost. Okay, so let's go ahead and work this out. So the curved surface, what is the surface area of a cylinder? This one's actually in your formula booklet. I'm going to go there real quick, and we'll speed up this one, I suppose, as well. So where are we? The curved surface of a cylinder. So geometry, trigonometry. Here we are. Area of a curved surface of a cone. We want the curved surface of a cylinder. Okay, let's see. Here we go. Area of a curved surface of a cylinder, and it is 2 pi r h. R is the radius, h is the height. 2 pi r h. Okay. So let's write this out. Area is equal to 2 pi r times h. And remember, h in this case is the height, but since our cylinder is itself on the side, this is actually equal to L. That's the curved surface, 2 pi r times L, plus the rectangular lid. The rectangular lid is just a rectangle, and it's r times L. So this is just r. Actually, one sec. It's not exactly just r times L. This is r, and this is r. So total distance we need to go is 2r. So if we want to find the total, if we want to find the area of this rectangle, a rectangle is of course length times width. The dimensions of this rectangle are 2r times L. All right. 2r times L. and then we have plus the semicircular ends. And we have, this is given to you in your formula booklet, of course, area is equal to pi r squared, but we don't have a full circle, so each of these are just, well, half. We have half of a circle, so it's pi r squared over 2, but we do have 2 halves of a circle, so essentially we have a full circle, and the area of a full circle is just given by pi r squared. So we have pi r squared. I just realized that I forgot something. This is the total area right here, and we need to, again, multiply this by $4.40. And here for our curved surface, or sorry, our semicircular ends, this we're just going to multiply by p. Okay, so good challenge so far. This is area of the curved surface, 2 pi r times h. H is itself L. Rectangular surface is just the dimensions of a rectangle, 2r times L. This is the total area right here, and it is 440 per square meter. This is our 2 semicircular ends. 2 half circles make a whole circle. This is our area right here, and it costs $p per square meter. Okay, so we're actually almost there, but if we look at the original formula, it's just in terms of r. There's no L, there's P, that's okay, so this should be able to stay. The R's should be able to stay, but we want to get rid of these L's right here. And remember, oftentimes, said this a few times, that the IB will often ask questions that lead into something else. They won't ask you something as a kind of piece of trivia or just to test a discrete skill. That will often lead into something else. And we found earlier that L was equal to 1.6 over pi r squared. And remember, this equals, whenever we see equals, it's essentially an is. L is equal to 1.6 over pi r squared. L is equal to 1.6 over pi r squared. L is 1.6 over pi r squared. So what does that tell us? That means that wherever we see an L, since L is 1.6 over pi r squared, we should be able to substitute this value for L. So let's go ahead and do that. So all of this is equal to 2 pi, and then L is equal to 1.6 over pi r squared. I'm actually going to use a color, 1.6 over pi r squared, because that's what L is. L is equal to 1.6 over pi r squared. We should be able to just substitute pi r, whoops, let me erase this, 2 pi r times L, and then L itself is right here, 1.6 over pi r squared, plus 2r, which is fine, but then we want to multiply and substitute, get rid of this L, and replace it with pi r squared. All of this, once again, multiplied by 440, plus, and then this can stay as it is. This is just pi r squared, no L's or anything like that. All right, and now we have to expand. Actually, to be honest, I'm going to try to look up and show you the mark scheme. I believe I have it here. If I don't find it within 10 seconds, then I will go on. Let's see, is this it? This is... This is not it. I'll try one more. One more. This is a paper 1. I'll try once more. I don't think this is it. Okay. I'm going to show you on the larger screen then. So here's the mark scheme actually right here. So after we write that out, there's some method marks right at the beginning. So area with L is replaced by 1.6 over pi r squared. And the question is, like, we've got this rather messy looking formula right at the end. And the question is, like, do you have to expand it to show that, hey, one thing is equal to the other? You don't actually. I mean, after all of the expansion, it's just a way to confirm that, yes, in the end, cost is equal to all of this business. So we have 440 times pi r, 1.6 over pi r squared, plus 440 times 2r, 1.6 over pi r squared, plus pi times pi r squared. Sorry, p, the price for that rectangular lid, times pi r squared. So you don't actually need to expand it. You just need to write it out after substituting L in for this. So here's the cost given by each of these formulas, which is kind of manageable, I think. And then L, if you're able to get that L at the beginning, or find the value of this length in terms of pi and r squared, substituting L for this, and then we're writing out the final value. Challenging question, no doubt, but I guess the positive thing is we don't need that final expansion to show that it all equals each other. Okay, let's go back to the document. Okay, so I don't think I'm actually going to expand this. Do I want to? No, that's okay. I think that's fine. After that, it leads to 7.04 r to the negative 1 plus 14.08 over pi r to the negative 1 once again plus pi, or sorry, not pi, p pi r squared. Okay. All right. Certainly a challenging question. Part C is asking you to find the derivative. So change in cost over change in the value of r, the radius. So as we stretch out the radius and make this kind of wider at the bottom or shrink it, how does that change the overall cost of these cylinders? So remember, dc over dr is the same as c prime, just like dy over dx is equal to y prime or f prime of x. Right? All of these things notationally mean the same thing. So dc over dr is a c prime. It means we want to take the derivative. So let's go ahead and take the derivative. Here's c. C is equal to, I'm actually just going to borrow this right here. There we go, that's good. And now let's take the derivative. Formula booklet has our derivative. I'm going to write it out real quick. If f of x is equal to x to the power of n, this is given in your formula booklet. Derivative is equal to n times x to the n minus 1. So we multiply by our exponent, and then our exponent reduces by 1. Let's give it a try here. C prime, which is the same as dc over dr, is equal to, let's take this negative exponent, multiply it out in front. We now have negative 7.04 r. R used to be negative 1. Now we're going to take away 1 from this, and now it's going to be negative 2. Plus, this is just some number. This is just some number. Pi is not a variable. Pi, remember, is equal to 3.1415 and so on, so on, so on. That's all I remember. 3.1415. Infinite number of digits, of course. So this is just some number. We don't need to do anything with this pi. It's just some number. What we need to focus on is this r value right here, this variable. And in this case, we just want to do the same thing. Take this r, multiply it out in front. And so now all of this business, this 14.08 over pi, is going to be multiplied by a negative. So this will actually become all negative. So negative 14.08 over pi r. R used to be -1, now it's -2. Plus, and now again, this is what makes, I think, this question more challenging. What do you do with this p? What do you do with this pi? P, remember, is the cost. We're not taking the derivative in terms of p, the cost, or anything like that. P is the cost. P stands for some number. It's some dollar amount that we don't know yet. It's fixed, though. It's not going to change. And if it's not going to change, it's just a constant, like a number. And so we don't take the derivative in terms of p and r. It's just some number. All of this is just some number. R is the thing that changes, and it's what we want to take the derivative of. So once again, dy dx, take the derivative in terms of x. Just deal with the x. dc dr, take the derivative of r. Everything else, leave it as it is. Just focus on the r in this case. Okay, so let's go ahead and take the derivative here. So focusing on the r squared, multiply it out in front. This becomes 2p pi. So we just took this exponent, multiplied it out in front. It used to be a 2. We take 1 away from it, and now it's 1. There it is. Challenging question, but I think it's a good question. Okay, let's continue on. So there's our derivative, and it's a good 3-mark question. All right, I think this is rounding out to the bottom. There's just a little more after. Okay. Let that go by. All right. The cost of materials to construct the container is minimized when the radius of the container r is 0.7 meters. Find the value of p. Wow. Okay. The cost of the materials to construct the container is minimized when the radius of the container r is 0.7 meters. Okay. So, what can we do? The cost of the container r is minimized when r is equal to 0.7. So when r is equal to 0.7, the cost of the container is minimized. I want to go back to the calculator and just give you some kind of conceptual understanding of what's going on here. This is our original cost function. Actually, sorry, back to the document. 1 sec. We have an equation for the cost, and we've also got an equation for the derivative, that is to say the change in the cost as we vary r. So remember, the derivative is just the change, the momentary change at a given point. So let's actually put in this cost function, and then we'll get an idea of the change in cost through time. So let's put that in on the calculator right here. So we have 7.04 r. Actually, sorry, we're going to need x. X to the -1 plus, set up a fraction, 14.08 over pi. And then this is again going to be multiplied by x to the -1. And then the problem here is we don't know what p is. So we can't just simply do pi times r. So we can't just simply do pi times x squared, because we have two variables. And that's a problem. So, I mean, as we, what do we know? We don't know the cost. We do know the final radius, but we don't know the price. So what's going to be challenging here is that we have the final cost we don't know. We just know it reaches a minimum. We know that the r value is going to be 0.7, but we don't know p, so we still have too many unknowns. So that one, we're not even going to be able to look at the function and see how it changes. We can get an idea, if we erase this, we can get an idea of what this might look like, this cost function, if the price were equal to $1, and so on and so on. Maybe even not too much of an idea. And then we could put in $2 and $3 and $4 and so on for different values of p, but this isn't going to be a way to solve it. We have too many variables. We don't know p. We can't substitute it. So what that means is we're going to actually need to use our derivative. So here it is. Let's go and bring this to the next page. I'm going to copy this, and then let's bring it here. Okay. So the cost of the materials to construct the container is minimized when the radius of the container is equal to 0.7. It's a good question. I think it is. So I'll draw an axis, a set of coordinates here. And what do we know? Something is minimized. If we have some function like this, actually going back to the calculator for a sec, we see our function as it looks like we're going to have an infinite amount of cost if we make our radius like super small. Like even though we don't have p here, the cost, if p is equal to 1, for example, the price of this rectangular lid is equal to 1, the cost for a very small radius is going to be massive. But there's going to be a point where we have a minimum right here. And then of course as we increase the size of the radius, the cost as a function of the radius, the cost starts to increase. It increases some more. So let's even work with this. So let's go back to the document for a sec. And we have cost as a function of the radius right here. And this is what we have for some value of p, but we don't know the value of p yet, so we can't actually use this function. But this is kind of what our function looks like. And remember, it can't be negative, so we're just dealing with this positive area where r is greater than 0, right? So just this side. And what do we know? The derivative itself gives us the slope of a line at a point, or the slope of a tangent line at a given point. So if we're looking at this point right here, for example, we have a negative slope. And if we look at this point right here, again we have a negative slope. But this point right here, a little further on, we have a negative slope. But there's going to be a point where we move from having a negative slope to having a slope of 0, where we don't have any increase or decrease, where essentially m, where the slope of the tangent line is equal to 0. And then of course we're going to have an increase again, and an increase, and so on at any point on the line. But as we go down, as we move from decreasing slope, before we start increasing again, before our cost starts increasing again, there's going to be a point at which it's stationary. So if you imagine, for example, if you wanted to track the height of some ball, you would want to find the point at which it stopped increasing, the maximum height of some ball. We would have some ball that would rise, it would increase, and there's going to be some stationary point, and that stationary point where it, in theory, is not moving up or down at all, is going to be, in theory, its maximum height, and then it's going to start decreasing once again. Here we have decreasing slope. Here we've got a slope of 0, and then it's going to change direction. And if we find out where this slope is equal to 0, then by definition we've found our minimum, because it's done all of the decreasing that it's ever going to do. And now it's eventually going to start increasing again. So where is the point where the slope is equal to 0? And what does that mean in terms of our derivative? All the derivative is, remember we call the derivative our slope function or gradient function. What that means is it gives us the slope of a tangent line at different points. It gives us the slope of the graph at different points. And what we're asking here is, okay, well, when is the slope equal to 0? We can put in different values of r. We can put in 1 or 10 and so on. But the question that we want to ask is, what is the value of r when this thing has a slope of 0? So set our derivative to 0, and this will find the minimum for us. When the slope is 0, we've reached the minimum. We've done all the decreasing we're going to do. We haven't yet started increasing. That's going to be the point where we have our minimum. Oftentimes these questions, if you have a derivative, sometimes it will be possible to use the original function, but oftentimes, especially on like a challenging paper too, where is something minimized or maximized? That is to say, where do you reach your maximum? Well, after you're done increasing, before you start decreasing. And where do you reach your minimum? After you're done decreasing, before you start increasing. So when m is equal to 0. So often when you see this minimize, maximize, set dy dx, or f of x, whatever it happens to be, f prime of x, set it equal to 0, and then just solve. Essentially end solve, really. Okay, so there it is. When is the derivative equal to 0? For this function of negative 7.0r, we know that it's minimized. That is to say, we know the slope is going to be 0 when r is equal to 0.7. So when r is equal to 0.7 to the negative 2, I'm going to get a little more space. When r is equal to 0.7 to the negative 2 minus 14.08 over pi, and then r is again 0.7 to the negative 2 plus 2p, and then this is just pi. Is that all it is? 2p pi? Our derivative, no, it's 2p pi r to the 1. So r2 and then becomes 1. So 2 pi r, and then r once again is equal to 0.7. Okay. Now we've got an equation just in terms of p. Pi is not a variable, so it's just a whole bunch of numbers and then one variable p. And then what we want to do is we want to end solve for all of this. So let's go ahead, and what we want to do is we want to end solve for p. Okay, so let's go into the calculator and work this out. This would definitely be one of those questions that you probably want to look over just to make sure that all of your numbers are correct. Negative 7.04 times 0.7, and we will raise the 0.7 to the power of negative 2. Brackets, in this case, don't actually matter. This is how I had written it. 0.7. Essentially, you just want the negative 2 applied to the 0.7. It doesn't matter in this case. Minus 14.08. Set a fraction. 14.08 over pi. And then again, this is 0.7 raised to the power of negative 2 plus, I just realized I forgot to numerical solve this. There we are. Okay. 0.70 is good. Negative 2 plus 2p times pi, and then r, which we know is 0.7. And then we want to ask the calculator to solve for, all of this is actually going to be equal to 0. So this is our derivative. 0 is equal to all of this business. And then we want the calculator to solve for p. So before I type this in, I'm actually going to just double check just to make sure this matches written. So derivative of 0 is equal to negative 7.04, 0.7 to the power of negative 2, 14 pi, good, plus 2 pi and this is 0.7 times p. Okay, there it is. It's fantastic. So find the value of p. P is the cost of this rectangular lid. So the cost of materials construct the minimized cost of materials to construct the container is minimized when the radius of the container is equal to r. So minimized, find the value of p. So we had just this p as an unknown. And therefore p is equal to 5.34622, or p is equal to 5.35. Okay, and then we can imagine it's dollars. Wow. Okay. Good question. Good question. Okay. Let's go on to question E. In total, 350 containers will be constructed at this minimum cost. Calculate the cost of materials to the nearest dollar to construct all 350 containers. Okay. So this is actually an interesting question. Calculate the cost of the materials to the nearest dollar to construct all 350 containers. So where is it? This is our cost function right here. We know what R is, and we can use that to find the cost. We know what P is, and we can use that to find the cost of a single container, and then we can multiply. That should work out okay. Yeah, it's a little unfortunate that a question which is, to be honest, not so challenging as an input-output if you just know your values and then multiply by 350 does itself depend on a previous question. I'm going to write this out just so we can substitute it in a little further below. R to the negative 1 plus 14.08 over pi r to the negative 1 plus p pi r squared. So this is a function which relates cost to the radius, and then of course it also has this value of p, which we do know now. Okay, so here we go. This is for part E. Calculate the cost of materials to the nearest dollar to construct 350. Okay, so we know what P is. We know R itself is equal to 0.7. So this actually isn't all that bad of a question, I suppose. 7.04 R is equal to 0.7. Raise that to the power of negative 1. 14.08 over pi. R is equal to 0.7 once again. Plus P, which we found out was 5.35. Times pi, and then this is just inputting this value of 0.7 in once again. So we know what P is, we know what R is, we have a cost which relates the cost of one cylinder to the radius, and then if we know P we can just substitute that in. So that would give us the cost of one cylinder. So let's go back to the calculator and work that out. It's tempting to actually just grab this. No, I can't in this instance. Okay, so let's type it in. 7.04 times 0.7 raised to the power of negative 1. Raised to the power of negative 1 plus, let's open up a fraction, 14.08 over pi multiplied by 0.7 raised to the power of negative 1 plus our value of P, which we found to be 5.35, multiplied by pi, and then 0.7 multiplied by 0.7 squared. And this is the cost of one cylinder. $24.69 and 54. So it's 24.6954. Let's write that out. Going back to the document here. Cost is equal to 24.6954. Cost is equal to $24.7. So $24.7 for one cylinder. And actually, let's keep all of our digits just because we haven't reached the final answer yet. So let's write it as 24.6954. Let's keep a fair bit of accuracy. That's the cost for one cylinder. But we don't want to know the cost just for one cylinder. We want to know the cost for 350 of these containers. So we want to take this, we want to take 24.6954 and multiply it by 350. And that will give us the total cost of the 350. So 24.6954 times 350. Oops. 24.6954 times 350. 6954 times 350 equals $8,643.39. Here, once again, often not a bad idea to check, especially on paper 2, but in general, especially on financial mathematics questions or when it comes to monetary amounts, money amounts, nearest dollar. So $8,643. All right, that is how much it would cost for 350 cylinders. All right, 895. Let me just make sure this is all good. 6954. 6954 looks good. 54. Okay, good. Yeah, let's leave it. Let's leave that one just like that. I think that's good. Okay, question 5 continued. The materials for constructing the containers can be purchased at a discount according to the information in the table. Determine the cost of materials for 350 containers after the discount is applied. So they can be purchased at a discount according to the information in the table. Cost of the materials before the discount. So we know we paid $8,643. $8,643, which means that we would be within this range. Determine the cost of the materials for 350 containers after the discount is applied. Okay, so we have to pay $8,643, $8,643, but we have an 8% discount. So let's take away 8% of 8,643. If you're comfortable as well, 8% is equal to 0.08, and 1 minus 0.08 is equal to 0.92, or essentially 92%. So we only pay 92% of the price because we're taking 8% away. If you're more comfortable with this, either way, I'm going to go ahead and type in 8643 times 0.92. This is going to give us a value of $7,951.56. All right. Determine the cost of 350 containers after the discount is applied. 3 sig figs. We would write this as 7950. Once again, 1, 2, 3. To be honest, a rather peculiar way to end a very complex question with a kind of simple discount, applying a discount. But overall, yeah, quite a good question. But a lot going on, certainly. Okay, everybody. I hope that was helpful. Remember, try to maximize process marks. Look for entry points where they are. So, for example, just going back to this one, looking at the derivative, that will be something that will help. Writing this in terms of, so L is equal to something. And we can write this out if they give us the volume. That would be, another possible entry point. Looking at this, find the value of p. If we know what the derivative is, hopefully this should be okay as well. Finding the point at which our slope is equal to 0. They're a fairly common kind of question, when is something maximized, minimized. So looking for those entry points are always possibilities. Okay. All right, everybody. I hope that was helpful, and as always, best of luck. Take care.